All right, folks. So this is basically a quick introduction to the DC motor model that you have already seen in the classroom. We've discussed this thoroughly, and then we've looked at how to develop the model. But I'm going to try to go through this model so that this serves as a review for you, as well as it's going to help you start working on your projects. Okay, so here you have the DC model, DC motor model, which has the electrical circuit, and then we have an electromechanical energy conversion happening here, and then here we have the mechanical component of the motor. Okay, so we know that now we can write two different differential equations for each of them, and then here we have a method to link those two equations so that we can represent the interrelated nature of those two equations. Okay, so how do we set these up and then how do we relate them? So let's first take a look at that, and then we're going to go look at the overall model that we're going to be using, that you're going to be using for the project. And I will leave the model reduction, I will leave the simplification process up to you for another video, or as you know, once you've tried this yourself. Okay, so these are the different things. So here we have the armature voltage, the current IA is armature current, the resistance represents the total resistance in the windings of the motor, then inductance is the total inductance of the winding. This is a permanent magnet DC motor. Okay, it's a PM DC motor. So therefore you will not see the field winding that you would typically see in other cases. But there is a back EMF because you have permanent magnets. Those will result in a back EMF. That's the EA term. And then once the energy conversion happens from electrical to mechanical, we have the electromagnetic torque. Okay, and that electromagnetic torque acts on this mechanical system. We have a load torque, and then we have inertia, which is J, and then B is your viscous damping or damping coefficient, okay, which is a speed related torque element that we have discussed again earlier. Okay, now moving on to the electrical equation. So if you go through this and apply a KVL, you see that we have VA equals RAIA LASIA plus EA. So it's basically this loop. So remember, now we are doing this analysis in S domain directly with initial conditions set to 0. Keep that in mind. Okay, and all these are Laplace domain variables. That makes our lives easy. So S here is the Laplace variable. Okay, typically this would be DIA over DT, but when you transform that into Laplace domain, you have S DIA, which is shown here. Okay, so this is the first equation, and then for us to go back to current, since our voltage, the armature voltage, is what we control, and then current is what we want to study as it links to the mechanical system, we're going to take this EA to the other side and then divide by the rest of the terms. So this is your first transfer function. You can see it's LASRA, meaning this is a first order system. Okay, all right. All right, maybe that's a little bit better. And now here we have the back EMF term, right? And then this is going to help us link to the mechanical system. Back EMF EA is related to KE, which is the back EMF constant times omega m. And we said that for a given motor, this constant is like, it means it's a constant. It does not change for what you are working on. This stays a constant. Okay, and then we also discussed another relationship, how this KE relates to KT, which we will discuss in a little bit. All right, so those are the electrical equations that we're going to need. And then here we have the mechanical equations. Okay, so mechanical equations, let's first of all focus on this equation. Okay, we have electromagnetic torque. So this is again applying our looking at our free body diagram and then setting the sum of torques equal to inertia times acceleration. So basically that's the idea here. We have electromagnetic torque. We have load torque opposing electromagnetic torque. So that's why it's on the right hand side. You could also write this as TE minus TL. Okay. And then we also have the damping component, B times omega M, the speed dependent torque component, and that results in J times the acceleration, which is S omega M. Again, this is in S domain. Okay. So from this equation, we want to highlight, or we want to extract the speed. So we're going to rewrite this equation in the following form. TE minus TL is equal to 1 over, or TE minus TL over JS plus B is equal to omega M. Again, this is a first order equation. Okay, that's a first order equation. Now then we have to look at what our electromagnetic torque is. This is where we make the link between the electrical and the mechanical system, at least one link. And you can see that this is torque constant. Again, it's constant for a motor, for our discussion at least. And the torque constant times current gives you the electromagnetic torque. The units here are Newton meters per amp. And then units for KE, SI units is volts per radians per second. Okay. So TE is KT times IA. So we have established the link from electrical to mechanical, and we discussed that KE is equal to KT, or almost equal to KT in SI units. Okay, in SI units. So that's why I've given you only one parameter, because now you can figure out the second parameter. Okay, so this is the relationship, and I want you to use the proper units in looking at these equations when you're modeling your system. Okay, so now since we have these equations, let's see what we can do here. So these are the 4 equations that you're going to be using to build your model. So at this point, I would pause the video and try to sketch the model, the block diagram first before you start doing something. Okay, because I'm going to show you how to set up that model in the next page. Okay, I'm going to walk all of you through that. So I would first try it before going through the rest of the video. Okay, all right. So here we want to first implement this equation. Okay, VA minus EA over LA plus RA. So let's say this is our EA. Okay, so let me tilt this a little bit. Okay, so this is our EA. Okay, and this is our armature voltage VA. Okay, VA minus EA passes through the transfer function 1 over LAS plus RA. Okay, LAS plus RA. That's this first equation, which gives us current. This is our armature current, IA. Okay, and then we know that armature current goes through KT. Okay, armature current becomes torque when it goes through KT, right? So IA times KT, now you have electromagnetic torque, TE. Okay, TE. And so that's when we think about the mechanical equation. See, there's TE now in conjunction with TL and inertia and damping, which gives us speed. So now we're going to implement this. So TE minus, so this is plus TE minus TL is what goes into the next mechanical transfer function. Mechanical transfer function. Okay, mechanical transfer function. And this is 1 over JS plus B. JS plus B. And in this case, the load and the back EMF, these are going to serve as disturbances for us as we go study this motor dynamics, and I'll show you how. Okay, so Js plus B, and then from here we get the output. Js plus B gives us speed. Okay, that's our omega m, that's our speed. So we have the speed that we're going to control by controlling the voltage. Okay, and load torque is out of control for us. All right, and we do have to make the final connection here, which is EA. Okay, it's Ke times omega m. So this is this back EMF term, and we're gonna sketch this right here. This is Ke, right? Ke, and we know that value already because we know Kt. Okay, so now we have the basic DC motor model that you're going to be using. Now in this model, two things are missing. Okay, the first is the gear ratio. It's not here. I want you to think about where to put the gear ratio. Okay, and then how you would represent that. That's the first thing. The second thing is you need to add a feedback loop, and then the sensor gain needs to be in that feedback path. Okay, that's also not there. So this is the second part I want you to think about. Okay, given this model, you will need to sketch out those things, implement the closed loop with these two including. Okay, and then you can think about how to go about simplifying this block diagram. Okay, how you can go about simplifying the block diagram, and that would be the next step for you. And I'm going to have another video that discusses those steps, but I first want you to try this and reach out to me if you have questions. Okay, all right, great. Sounds good, folks. Hopefully this will help you get started, and keep those questions coming. Thank you.